Okay, I would like now to go on with a new topic, and that's the topic of conditional quantiles. The moment that we are going to look at conditional quantiles, it's important to realize that conditional random variables are actually random variables themselves. They are, of course, conditional on the outcome of another random variable, but we should see them as random variables themselves, and that implies, among other things, that they are fully characterized by their distribution function. And we do know that the conditional distribution function is the distribution function of the random variable conditional on the outcome of another random variable. Let's look a little bit at a notation. We have the, distribution function of y1 conditional on this x1 that we have over here. We're going to evaluate it at the level of y and conditional on our x1 exactly equal to x. And that is by definition equal to the probability that y1 is smaller or equal to y conditional on x1 equal to x. Well, this is something that you have already seen, but this is just notation. And then also notation is the conditional quantile. For the conditional quantile, I'm going to use another time the q with the subscript tau that we already know of. We have y1. But now, in order to, show that this is the conditional quantile of y1 and not the quantile of y1 itself, we are going to have here x1 exactly equal to x. And what is that? Well, what we're going to get is exactly the same thing. What we're going to get is that the quantile is that number that is going to make the probability that y1 is smaller or equal to that particular number. Now, of course, conditional on x1 equal to x, that must be equal to tau. That is what we're going to get, and we should realize that this is exactly the same as what we had before with the unconditional quantiles. We can also do this in terms of distribution functions. Then, of course, we're going to see that it is that number that at the moment that we're going to evaluate the conditional distribution function in that particular number, that we are going to get a tau over here. Well, then again, what we can do is that we can take from the left and the right hand side inverses in order to get that the conditional quantile of y1 conditional on x1 equal to x is nothing else as the inverse distribution function, of y1 conditional on x1 evaluated in tau. Well, in order to look at this graphically, now what we are going to get is another time on the x-axis we're going to get our y's, and on the y-axis another time we're going to have now, in this case of course, the conditional distribution and not the distribution of y1 itself. Well, suppose again that this is going to be now our distribution function. Well, then again, it's not that difficult to understand that at the moment that we would like to look at the median, that we have to start here at the level of 0.5, then we go all the way over here, and then we find out that our conditional quantile is going to be this thing that we have over here. Well, we can do this now also for another level of x1. We have assumed that the distribution function of this one that we have over here is the conditional distribution function at the moment that x1 is equal to little x0 that we have over there. But we can, of course, look also at the situation in which x1 is not equal to x0, but for example, equal to x1. And we assume now that we are going to get this distribution function that we have over here. It's in this case a distribution function that just is shifted to the right. So that is the impact that the change in x1 has in this case. And we are going to see that we're simply going to get a shift towards the right. We can think of this particular case as, x1 being equal to x0 as being the distribution function that we have for women, and then the distribution function that we're going to have for men is this one that we have over here, where x1 is equal to this little x1 that we have over there. So this is somewhat comparable to the example that we have seen before. Now, what we can do is that we can look at the quantile, well, in this case, the median, for this situation in which x1 is equal to little x1. Well, then we have to go all the way over here, and then we're going to see that this is now going to be our new median, which is higher, of course, than the old one that we had because of the fact that the old one was somewhere over here. So we do see that the change from x0 to x1 is going to increase, in fact, the quantile. Well, we can do exactly the same thing as at the moment that we are going to look at the third quartile. Then we have to start here at 0.75. Then we go all the way over here. Then we see that the quantile at the moment that x1 is equal to x0 is this thing that we're over here. And we can also look at the situation in which, well, our x1 is equal to this little x1 that we're over here. And we get another time somewhat higher. So we do see that because of the fact that the distribution function of, say, x1 equal to little x1, so the blue distribution function is to the right of the red one, we do always see that the quantiles of, say, x1 equal to x1 always a little bit higher than those of x1 equal to x0. Well, we see even in this particular case that actually the difference that we have over here, it was exactly equal to the difference that we had here with respect to the median. And well, if I would have done this for the first quartile, also there we would have seen that there would have been exactly the same difference. And the reason why this is true is because of the fact that, well, I don't think that it's any surprise to you that what I have done over here is that I actually have just drawn here the normal distribution function. And the only thing that I have done is that I actually shifted the normal distribution function simply by increasing the mean. And therefore, because of the fact that we have shifted the distribution function, not we have necessarily a normal distribution, I could have shifted any other distribution function as well. We should realize that because of the fact that we shifted the, say, distribution function over here, that implies by itself that we always are going to have exactly the same differences in terms of the quantiles. So that might imply in this particular case that it doesn't make that much sense to actually look at the different levels of quantiles because of the fact that we would like to look at the impact of what x1 has. At the moment that we're going to change it from x0 to x1, well then we could just here focus on the mean, or on the median better to say, and then at that moment in time we can actually also know what it actually is at the moment that we're going to look at 0.75, or for example here at 0.25. Well, but that is not completely true. In this particular case that is true, but we should take into account that is generally not true. We could have situations in which the quantiles or the difference in the quantiles could be widely different between, say, two distributions. And that's, for example, the case at the moment that we're going to now look at this picture that we've over here. What I've done over here is essentially that I have here drawn another normal distribution, this red one that we've over here. The blue one is actually also a normal distribution, but it's now a normal distribution that has exactly the same mean, but a higher variance. Well, now at this moment in time, it might not be so good to make a comparison between women and men, for example, to make an example. But what we could have done here is that we're going to look at different regions. We could, for example, now look at a situation in which we are going to compare, for example, the Netherlands with the United States. Again, what we can do is that we can look at income. And even though the median income between individuals that we have in the United States and the Netherlands might be more or less the same, I'm not exactly sure whether that's actually true, but we should realize that there is a higher variance in the United States compared to the Netherlands. So therefore, at this moment in time, if we're going to compare these distributions with each other, then the first thing we can do is that we can look at the median. At the moment that we're going to look at the median, then we are going to make a conclusion here that the quantiles are exactly the same. So here, in this case, we could actually say that the quantile gap here between here, again, x1 equal to x0 and x1 equal to little x1, well, that quantile gap is here completely equal to 0. But that doesn't mean that any, say, difference in terms of the quantiles is exactly equal to 0. example, we can now look at 0.75. The moment that we're going to look now at 0.75, then we do actually see that the quantile, the third quartile here for, say, y1 conditional on x1 equal to little x1 is much higher than what we have actually in the case that we're going to look at the, say, subpopulation for which x1 is equal to little x0. So therefore, again, coming back to the example that we have seen before, even though, well, the median between the United States and the Netherlands might be more or less the same, we should realize that it could be the case that, well, at the moment that we're going to look at the higher incomes in the United States, well, maybe it's not that surprising that the higher incomes in the United States are much higher than what we have in the Netherlands. However, if we now would have looked at the first quartile, I'm not going to do that, then you're going to see that it's exactly the other way around. So therefore, concluding from this, we do see that if we do not just shift distributions from the left and the right, which is of course a very special case, but at the moment that we're also going to change the shape of the distributions, which is very likely to be true. It's very likely to be true that changing, say, the axis, changing x1, so looking at another subpopulation, doesn't only change the distribution in the sense that it's going to be shifted to the left and the right, but it may also change completely the shape of the distribution. And then what we're going to see, that it really matters where we are looking in the distribution, at what quantile in the distribution we're going to look at. I would like to now go on with a next topic. Well, that's actually a topic that we have already looked at before, and that's the so-called random coefficients model. We do already know that the random coefficients model looks like this. We have yi at left hand side, and we have xi times beta ui at the right hand side. Again, we are going to assume that ui and xi, they're going to be iid. And I'm even going to assume that u1, but of course then every ui, is going to be standard uniform. So therefore also xi and ui, they are also going to be independent from each other. So we have a very standard, say, random coefficients model. However, I'm going to make one additional assumption, and that is that I'm going to assume here that x multiplied by beta u, it must be strictly increasing in u. So therefore, we do not, of course, know what these betas are, but we're going to assume that it's in such a way that at the moment I'm going to increase u, then x times beta u must be increasing. Must also be increasing. Well, we could even look at a more general model. We could even look at a model in which we have here y at left hand side, and on the right hand side we have simply a function that is a function of xi and ui. This is even a more general model than the random coefficients model that we have over here. What we could do is that we could now make the assumption again that well, this function g that we have over here, that it's at least increasing in its second argument. So at the moment again that I'm going to increase u, then I also should increase this g that we have over here. Well, note that this is a very general specification and that the random coefficients model is just a special case, because of the fact that if I'm going to write my model now as gxu is equal to x times beta u, well then of course we're back in the random coefficients model. But based on this model we can look at the, say, conditional quantiles. For that, the best thing to do is to first of all look at the probability y1 is smaller or equal to q conditional on x1 equal to x. What is that? Well, then the only thing that we need to do is to substitute in the model that we had the previous slide. So therefore what we're going to get then is, well, y1 is equal to gx1 u1. So therefore we can also look here at the probability that gx1 u1 is smaller or equal to q conditional on x1 equal to x. Well, then the next step is a very standard one. This x1 that we have over here is equal to that x1 that we have over there. That one is equal to little x. So therefore this thing also is going to be equal to little x. So we can therefore write it like this. This is a very nice way to represent it, because now we should realize that even though here I still had that, well, this g that we have here at the left hand side, it's actually a function of two random variables, x1 and u1. But we should take into account that at the moment that we are going to look at this thing over here, well, this thing over here is just only a random variable, this u1. So this thing that we have over here is only random because of the fact that u1 is random. Well, now we can use a trick. We do already know that this g1, or this g function that we have over here, it's strictly increasing in u1. So therefore we can take from the left and the right hand side, we can take the inverse. If we're going to do that, then we're going to see that we have here the probability u1 is smaller or equal to this thing over here, the g inverse, evaluating x and q. Well, we are going to get this relationship now over here. Now we should realize that what we have over here is no longer the distribution of y1, but it's the distribution of u1. So therefore we can actually write it as the conditional distribution of u1, conditional x1, evaluating this value over here, and x1 of course is equal to this x over here. But we do know that u1, it is uniformly distributed and also independent from x1, so therefore we can even write it like this thing over here. We do know that if something is uniformly distributed, then it is just equal to where we evaluate it. So therefore we can simply write it like this. Well, now what we can do is that we can now look at the definition of a conditional quantile. We already know that conditional quantile is always the number that makes this probability that we have here at the right hand side equal to tau. But now we should realize that what we have here at the right hand side is exactly the same as what we have here at the left hand side, with the only difference that we here have a general q, and here we have the quantile, the conditional quantile over here. But that means, of course, that I can rewrite this right hand side of over here as the right hand side of over there, where we are simply going to replace the q by this quantile that is over there. So therefore I can also write it like this. Well, this is a very nice representation. Now what I can do is that I can another time take an inverse. Now I'm going to take the inverse of this g function that we have over here. That's of course the g function itself. If I'm going to then do this from the left and the right hand side, then at the left hand side I'm going to have gx tau. That's actually written now over here at the right hand side. And well, if I take the inverse of the inverse and evaluate an inverse itself, then I just get back this argument that we have over here, this q, this quantile that we have over here. So therefore it says now that the quantile of y1, conditional x1 equal to x, is simply equal to this gx tau that we have over here. And then we are particularly interested in the random coefficients model, then we're going to see that what we're going to get is actually nothing else as x beta u. So then the conditional quantile is actually nothing else as x beta tau. Well, this is very interesting because of the fact that we now have a good interpretation of the beta coefficients that we have with respect to the random coefficients model. Remember, for a long time ago, that we do know that the beta coefficients in a linear regression model, well, they actually say how much the conditional mean is going to change at the moment that we're going to change the x variable. That's an important thing that we already know for a very long period of time at the moment that we're going to look at a linear regression model. That's the interpretation of our beta coefficients. But now we should realize that now at the moment that we're going to look at the random coefficients model, then our, beta coefficients that we have over here are going to show how the conditional quantile is going to change at the moment that we're going to change the x's. So for example, if I'm going to change this x by 1, then my conditional quantile, for example, the conditional median, is going to increase by beta tau. And that actually gives us more or less the same interpretation that we do actually have from, standard linear regression models. But now with respect to the conditional quantiles rather than the conditional mean. Well, this, but also many other reasons, resulted in the fact that Kunker and Bassett, already in a Econometrica paper in 1978, introduced quantile regression. Well, this is a very old paper, and I don't recommend you to actually read it. reason behind that is not only because of the fact that it's very old, but it's also very difficult to read. And well, there's nothing bad with reading difficult papers, but you should also take into account that probably because of the fact that it's so old, lots of things that are written there are, well, actually not only very technical, but they're also not that relevant anymore. If you would like to know something about, say, quantum regression, I would say in the very first decades of quantum regression, then it's better to use this article over here. This is by Baczynski, also a relatively old article, not as old as that one, 1998, in the Journal of Human Resources. There he actually looks at, well, a lot of things related to quantum regression up till, say, well, the turn of the last century. Well, what they do, and that's actually the most important thing to say about this paper of Kunkel and Bassett, is that they assume that we are going to have that the conditional quantiles, y1 conditional x1 equal to x, are exactly equal to x times beta tau. This is exactly what we have seen from the previous slide. We do see that the random coefficients model actually does have this property. But take into account that Kunkel and Bassett actually did have a little bit of a different view with respect to this. They did not really think in terms of random coefficients model. I don't think that a lot of people actually looked already at random coefficients model at the time of 1978. What they just did was that they said, like, well, suppose that we have, say, a model for which it is true that at the moment that we're going to look at the conditional quantiles, y1 conditional x1 equal to x, that we can write them as x times beta tau. That's just here an assumption. It's not a result from a particular kind of model as we have seen at the previous slide. But we do know that the random coefficients model actually has this property that is over here. We'll later on see that there is actually also a relationship with respect to the linear regression model. However, I would like to look first at an intermezzo with respect to identification. For that, we have another time on the x-axis we have the different values of y, and on the y-axis we have the distribution function of y1 conditional on x1. Well, then let's assume first of all that we have a situation in which x1 is equal to little x0, and let's assume that the distribution function that belongs to that situation looks like the red one that we have over here. Well, then as usual we can look at the median, which means of course that we have to start here at 0.5, and then we go all the way and go down here over, and we are going to see that we have here the median of y1 conditional on x1 equal to x0. Take into account that with respect to identification, this thing is assumed to be known. And that's very important in econometrics. Now, I'm not that sure whether you have had identification before during your econometrics lectures. I'm pretty sure that somebody has been talking about identification, but I'm not that sure whether you already know why it is so important and what it actually is. Well, the thing with respect to identification is that we are going to ask ourselves the question, well, maybe better to say, in econometrics, we typically try to estimate objects or parameters. And an important question that we have to ask, or could ask, is whether we could actually estimate those parameters. Does the data that we have at hand, is it informative enough in order to know or be able to estimate the things that we want to estimate? Well, in that sense, it's important to realize that what do we actually assume with respect to data at the moment that we think in terms of an econometrician? Well, the answer to that is that at the moment that we think about data sets, then we don't think really about the things that we usually have stored in our computers. For example, in a Stata data file or something like that. Even though these are called data files, as econometricians we do have the idea that data is something else. And data actually comes to us in a random way. It's a random process that comes to us that has a particular, what we typically say, well, data generating process. And that comes to us in a random way, and of course the thing that we then have stored on our computers is nothing else as a realization with respect to that particular random process. But we should take that into account that our data is actually nothing else as a set of stochastic variables, and as usual stochastic variables do have, say, a distribution function. And then an important question that arises is, what can we actually then know about the data? What is the most we can ever know about a data set? Well, the answer to that is, of course, not the things that you have stored on your computers. But the answer to that is that the most we can ever know about a data set, a random variable or a set of random variables, is its distribution function. We do already know for a long time that the most we can ever know about a random variable is its distribution function. If we know the distribution function, then we know everything about a random variable. So therefore, the obvious answer to the question, what can we ever know about a data set, is of course its distribution function. In general, we don't know it. In general, we only have a realization of our, say, data, which is stored on our computer. But we can ask ourselves the question, suppose that we know everything that we ever can know about a data set. That is, of course, its distribution function. Well, then, in that case, we can ask ourselves the question, what could we then actually estimate, or do we then actually know the things that we want to estimate? Because at the moment that we even do not know what the thing is that we want to estimate, at the moment that we know the data distribution, then, well, the question arises, can we ever know it apart from guessing? So therefore, identification in econometrics is important. And what you actually do at the moment that you are going to look for identification is that you're going to simply ask yourself the question, suppose that I know the data distribution, does that mean then that I know the things that I want to estimate? Well, that is an intermezzo with respect to identification, but then the question of course arises, how is that related to the thing that we have over here? Well, it's related because of the fact that this thing I just said is known at the moment, or at least assumed to be known, at the moment that we think in terms of identification. And the reason behind that is, of course, because of the fact that we do know that y1 and x1, they belong to the data. That is something that we observe at the moment that we have the data. So therefore they belong in sense to the data distribution. But we should realize that, well, then we also know the inverse of that particular distribution, which is actually this thing that we have over here. So therefore we should realize that at the moment that we are going to think about identification, we could assume that this thing that we have over here is known. But what is this thing that we have over here? Well, according to the assumptions that we have made with respect to the quantum regression model, we do know that it's equal to beta 0, evaluated in half, plus x0, this x0 that we have over there, multiplied by beta 1, evaluated in half. At least if we are going to assume that we just have a constant and say a, well, coefficient for this x1 that we have over there, well, of course, at our median regression, well, then we have this situation that we have over here. Take into account that this is not enough for identification because of the fact that even if we know this thing that we have over here, it will be impossible to know both beta 0 and beta 1 because of the fact that we have here, well, two unknowns in just one particular restriction. So therefore the question arises, how can we prove in fact identification in this case? Well, suppose now that we, apart from an outcome of x1 equal to x0, there is also the possibility that we have an outcome, well, of x1 equal to little x1. And suppose that the distribution function that belongs to that is this distribution function that we have over here. Again, this thing that we have over here is known at the moment, or at least assumed to be known, at the moment that we think about identification. In this case, it's also not important that it's just a, say, a shift to the right. of the original distribution function that we already had. That's not that important. What is the most important is that we just have another distribution function. It wouldn't be so nice if it would have been exactly the same, but we have now another distribution function. And then we can do exactly the same. We can now start here at a half, go all the way now over here, and realize that the, say, quantile that we have in this particular case is equal to this thing over here, the median that we have in this case, because we look, of course, at 0.5. But also this thing can assume to be known at the moment that we think in terms of identification. But also here we do know that according to the assumption that we have made, the, say, assumption with respect to quantile regression, this must be equal to beta 0, evaluated half, of course, again, plus x1, again, this x1 over there, multiplied by beta 1, evaluated in 0.5. Well, this is now going to be helpful, because one thing that we now can do is to combine these two restrictions that we have over here in order to at least show that beta 1 is identified, because one thing I can simply do, well, is to subtract, say, these two things from each other. If I'm going to do that, then I get at the left hand side, I get the differences in terms of the quantiles, and on the right hand side I simply get x1 beta 1 evaluated in half minus x0 beta 1 evaluated in half. And then we should realize that if we then divide the left and the right hand side by x1 minus x0, well, then we simply get this relationship that we have over here. And then what we can do is that we can, of course, then divide the left and right hand side by x1 minus x0, and then we get this relationship that we have over here. And now we actually have proven that our beta coefficient is identified, and the reason behind that is because of the fact that these two things, they are known at the moment that we know the data distribution, and this difference over here, well, it's just a given difference, it's just these two x's that we have over here, so therefore we do know that, well, if we would have known the data distribution, then we know this thing that we have here as well, i.e. we have proven that we have identification. I would like now to go on with the next topic, and that's the topic of the relationship with the linear regression model. We have already seen that at the moment that we're going to look at the random coefficients model, that the random coefficients model is actually nothing else a special case of the, say, quantile regression model. However, there's also a relationship with the standard linear regression model. This was actually the relationship that got much more attention, say, in the beginning years of quantile regression analysis. So therefore, suppose that we have here our linear regression model. We have yi is equal to xi beta plus ui. So a very simple model that we have over here. We're going to assume that u and x, they're going to be uncorrelated with each other. x1 contains a constant, and therefore we also have that this thing over here has a mean equal to 0. And now the question arises, how can we now look at the quantiles of this model that we have over here? Well, for that we can use or look first of all at this probability that we have over here. The probability that y1 is smaller or equal to y conditional on x1 equal to x. Then the first thing that we can do is that we can simply substitute in here the model that we do over here. And then we get this thing here at the right hand side, the probability that x1, well, beta plus u1 smaller or equal to y conditional on x1 equal to x. Then a very standard trick, of course, is that here we have an x1, there we have also an x1, but here it's equal to x, or little x. So therefore also this thing over here is equal to little x. So therefore I can write it like this. I can also bring this now to the other side in order to realize that what I have now is the probability that u1 is smaller or equal to y minus x times beta, conditional on x1 equal to x. Well, now we should realize that we have now is actually the distribution of u1 conditional on x1. So we can also write this as the distribution of u1 conditional on x1, of course evaluated in y minus x times beta, and conditional still on this x that we have over here. Take into account that we cannot get rid of this x over here, even though it's very tempting to just say like, well, let's just take this x away. But that's not allowed. And the reason behind that is because of the fact that even though we have assumed that u and x, they're uncorrelated to each other, we did not assume here that they're independent from each other. In order to get rid of this x that we have over here, I must assume independence, which is stronger than the fact that they're just uncorrelated with each other. So therefore, I cannot do that much more, anything more here than what I have already done over here. But now I can relate that to the quantiles of y conditional on x1 equal to x for this model that we have over here. Now we can realize that by definition a conditional quantile is nothing else as that number that makes this probability that we have over here, probability y1, is smaller or equal to that number, conditional of course on x1 equal to x, it must make it equal to tau. Now we should realize that we have here at the left hand side is exactly equal to what we have there at the left hand side, with of course the only difference that we have here the quantile and there we had the general y. But then what I can do is that I can just use here the right hand side where I'm going to substitute for y, I'm going to substitute this quantile that we have over there. That's exactly what I'm going to do first. I'm going to simply now look at this relationship that we have over here. I have it here actually another time. And then what I can do is that I can now realize that the distribution function of u1 conditional on x1, let's assume it to be completely continuous. So therefore it's upward sloping, it's strictly upward sloping. And that means of course that we can take from the left and right hand side, we can take inverses. So therefore we can also write it like this. We have now the quantile of y1 conditional on x1 equal to x minus x times beta is now the inverse distribution function of u1 conditional on x1 evaluated in tau. I can immediately bring this x beta, I can bring it to the other side in order to get now this relationship over here. And I can also realize that this is actually nothing else as the conditional quantile now of u1 conditional on x1 equal to x. So I can even write it like this thing now that we have over here. But one thing we already know is that in the standard regression or quantile regression framework, we do assume that the quantiles of y1 conditional on x1 equal to x, they're equal to x times beta tau. One thing that I have already mentioned a couple of times before is that this has a nice relationship between how in fact beta tau is going to affect, or maybe better to say how x is going to affect the quantile that we have over there. That is to say that what we can do is that we can take first order derivatives with respect to x, and then we do find that beta tau is the first order derivative with respect to our quantiles. At the moment that we're going to change the x's, then we should realize that the difference that we're going to get with respect to our quantiles is simply equal to beta tau. So that's quite nice. At the moment that I'm going to increase my x1 by 1, then at that moment in time, my conditional quantile, for whatever tau is going to increase by this beta tau that we have over there. Well, this is a quite nice relationship. But what we can do is that we can, now ask ourselves the question, how does that relate to this thing that we have over here? What is this thing over here at the moment that we're going to take the first order derivative? Well, that we cannot do here as well. That's not that difficult, of course. That we get here a beta. And we get the first order derivative of, say, the quantile of u1 conditional on x1 equal to x with respect to x. These two things are not generally the same. So that means that the, say, regression quantiles that we get with respect to quantile regression are therefore not the same, even at the moment that we are going to have a linear regression model. They're not going to be the same as the beta coefficients that we have from our linear regression model. It's going to be beta plus something. So as long as this something that we have over here is not equal to 0, then these two things are not exactly equal to each other. But there is of course a special case. At the moment that u1 and x1, they're independent from each other, well then you should realize that that of course also means that the quantiles of u1 no longer depend on x1. That's quite simple to understand. You should realize that at the moment that we're going to make this assumption, u1 independent from x1, then we assume that the distribution function of u1 no longer depends on the outcomes of x1. But that means, of course, as well that the inverse distribution function also no longer depends on x1. And since the quantiles are nothing else as inverse distribution functions, we should realize that that, of course, means that the quantiles of u1, then conditional on x1 equal to x, they're simply equal to their own quantiles without conditioning. But that means, of course, that this part of over here then simply becomes equal to 0. And that means, of course, that in that particular situation, if u1 and x1, they're independent from each other, then the regression quantiles that we have over here are exactly equal to the beta coefficients that we have from our, say, linear regression model. This is quite important, because of the fact that this implies that, well, the main question, of course, that arises is when do we actually have that u1 and x1, they are not independent from each other, but they are uncorrelated with each other, because of the fact that in our linear regression model we had the previous slide, I assumed that u1 and x1, they were uncorrelated with each other, but I did not generally make the assumption that they were, say, independent from each other. Well, that means, of course, that even though the, say, first moment of u1 conditional x1 is equal to 0, that doesn't hold true for the higher order moments. And even though, of course, any higher order moment could be different, it is, of course, it makes more sense to focus on the second moment. And what does it mean that the second moment of u1 depends on x1, however, the first moment doesn't? Well, that has a very special name in econometrics. That is called heteroscedasticity. So at the moment that we have heteroscedasticity, so then, of course, we do have that u1 is not independent from x1, because of the fact that the second moment depends on x1. Then at that moment in time, we do see that, say, regression quantiles are different from, say, the linear regression quantiles. That means nothing else is that, well, we need actually, in order for the regression quantiles to be different from the linear regression quantiles, in the linear regression model, we actually need heteroscedasticity in order not all these, say, regression quantiles to be the same and to be equal to the linear regression quantiles, so the beta coefficient that we have over here. Because if there is no heteroscedasticity, and also, say, all the other higher order, say, terms, the higher order moments are going to be equal to 0, well, then u and x are independent from each other. And then in that moment in time, generally we will have that beta tau is going to be equal to beta for any tau that we have over here. So that means essentially nothing else is that in that particular case, we simply are going to have that at the moment that we're going to run an ordinary squares regression, or at the moment that we're going to use quantile regression analysis, then we more or less get exactly the same outcomes. Of course, given the fact that we are going to estimate, so that means that we're going to have random variables, and it depends on the data. It may be possible that, say, just based on luck, some of the regression quantiles are going to be somewhat different, and they may be a little bit different from the ordinary squares coefficients that we're going to estimate. Generally, they will actually be the same. So you may even say, in that particular situation, if u and x are independent from each other, it doesn't make any sense to do quantile regression in that particular situation, because we can actually already get all the regression quantiles in that specific case by just doing ordinary squares. Well, this is, of course, generally not true. We can generally expect that there is some heteroscedasticity, and that's already enough in order to have that the beta coefficients of quantile regression are different from those from linear regression. Therefore, it makes sense to do quantile regression analysis. But of course, it could be the case that we are going to be in a very special case of no heteroscedasticity, and also the higher order moments, they are equal to 0. Then in that particular situation, the question arises, what should you do? Should you do ordinary squares, or should you do quantile regression? Well, the obvious answer with respect to that question is, well, ordinary squares is so much simpler than quantile regression analysis, so just do ordinary squares in that particular case. However, there is, say, an exception with respect to that rule. And that is in the case of outliers. We have already seen before that quantiles are actually more robust with respect to outliers. Well, that's actually also true at the moment that we're going to look at quantile regression. Quantile regression is very robust against outliers. So therefore, if you do expect a lot of outliers, then it might be still good to do quantile regression in this particular case, rather than ordinary squares, even in the case that there is, say, independence between u1 and x1. I would like to go on with the next topic, and that's the topic of the estimation of the quantile regression model. We have already been looking at the identification of the quantile regression model, but we haven't said anything yet about the estimation. Well, in order to start with that, it is important to recap that we already know that for any random variable set, we can write the condition, or the quantiles themselves, we can write them as the argument that is going to minimize this criterion function that we have over here. So that is of course then also true at the moment that we're going to look at a conditional quantile. Take into account that a, well, conditional random variable is nothing else as a random variable itself, of course, conditional on the outcome of another random variable, in this case y1 conditional on x1 equal to x. So that implies that we can, well, look at the conditional quantiles in exactly the same way as the quantiles that we have over here. So therefore, the conditional quantiles should also be, well, minimizing a particular criterion function. But the only difference is that here what we are going to have is not we have z, but we have y, and we have y conditional on x. So therefore we get here that the supports, well, they may of course be dependent on the outcome of x. And in addition to that, we're also going to look here at the, say, conditional densities rather than densities themselves. But apart from that, we have exactly the same as what we had before. Well, then what we can do is that we can then look at the fact that we do already know that the conditional quantile of y1 conditional x1 equal to x, that's always equal to x times beta tau. So therefore, substituting that in, based on the, well, equation that we had in the previous slide, we can also see that x times beta tau should be minimizing this thing over here. That is by definition the case because of the fact that we have made this assumption that we have over here. Well, and then we should realize, of course, that in this particular case, well, of course, what we could do is that we could minimize with respect to x multiplied by b, but take into account that x is actually given for us. X is just a particular, say, combination of the x1s that we have over here, and we do know that this actually should hold true for any kind of x, which means, of course, that x is essentially given for us. So that means that the minimization, even though we can do it with respect to x multiplied by b, it's more like a minimization that is with respect to b itself, say a vector of coefficients. So therefore we can actually also write it like this. We can also say that what we are going to do is that we're going to, well, have beta tau, we're looking for beta tau, which is the minimum of this thing that we have now over here. Well, now we can rewrite this a little bit. What I would like to do in the end is that I would like to write this just as one particular integral, not two integrals, but just one integral. How can I do that? Well, I can do that by, well, integrating over exactly the same range, over the same area that we have over here. That's not the case right now, but what I can do is that instead of integrating only from xb up till the supremum, I can also integrate over the full support of y conditional x. However, then I have to realize, or then I have to restrict this to be only, say, different from 0 at the moment that y is larger or equal to x times b. So therefore what I need then is an indicator function. Well, that's one thing that we have already looked at before. However, usually we did it the other way around. I can do exactly the same thing with respect to this integral that we have over here. I can integrate over the full support of y conditional on x, but then what I need to do is that I again have to use an indicator function, but now an indicator function that says that, well, y should be smaller than x times b. So therefore we can write it like this thing that we have over here. Then the next thing that I can do is that I can well, now I can of course bring these integrals together. But in addition to that, what I have done as well is that I have taken this density function that we have over here, I have taken it within the parentheses. So then in one step we are going to get now this long integral that we have over here. Well, now the most important step is that we should realize that this actually holds true for any level of x. So any x that we're going to get, we can actually do this minimization that we have over here. Well, that means, of course, that if we're going to sum over potential x's that we have in the support of this x1 that we have over here, then that should actually also be true. If I'm going to sum over 2 or 3 or 4, or maybe even 10 or a million different outcomes of this x1 that we have over here, well, then we should also have that all the sum over there should also minimize with respect to b. Well, that's the idea behind this equation that we have over here. Instead of summation, what we can do as well is that we can use integration. So here we're going to integrate over the values with respect to x. If we're going to do that, then we have here the marginal density. I could actually have done it here simply with dx, but we can also place here the marginal density of x1 over here. Well, the reason why I'm going to do that is because of the fact that here we have a conditional density and we multiply it by the marginal. That means, of course, that what we're going to get over here is the joint density of y and x. The conditional multiplied by the marginal is always equal to the joint. So therefore we can also write it like this. And now we should realize that what we have over here is actually nothing else as a population mean. It's a population mean because of the fact that we integrate over the variables that we have, x and y, over its full support, and we multiply the function that we have over here, we multiply it actually by the density function that we have over there. So therefore you should realize that what we now have over here is actually a population mean. So therefore we can also write it as a population mean, so we can even write it in the way that we have it over here. Well, this is very nice, the way I've written it over here. And the reason behind that is because of the fact that, well, at least theoretically, if we know this same mean for any b that we have over there, then we can actually minimize this and get the beta tau coefficients. But of course, we do not know how this function looks like, because in order to know this mean that we have over here, we need, of course, the, well, joint density of y1 and x1, as we have already seen over here. So that doesn't work, but the reason why we want to write it like this is actually because of the fact that now we see that it's a population mean, and that means that it could be estimated consistently by its corresponding sample mean. That means no, say, expectation, but we're going to have a summation. We're going to sum over all the observations that we have, and we divide by n in order to get now this thing that we have over here. And now we can do exactly the same thing as what we did with respect to the quantile itself. Now we should realize that this thing that we have over here, it's a sample mean, so therefore it's going to converge to its corresponding population mean, which is by definition, of course, equal to this thing that we have over here. Well, that actually holds true for any level of b, which means that if n goes to infinity, then this function that we have over here is, well, going to converge in probability to that function that we have over there. So that means that if n goes to infinity, well, essentially, this function over here is exactly the same function as that function that we have over there. Well, but then we should also realize that if we have the same functions, then they should also have the same minima. And therefore we should realize that, of course, the minimum that we're going to have over here, let's call it beta hat tau, should converge to the minimum that we have over there, from which we do know that's actually equal to beta tau. So that means that if we're going to use this, say, feasible estimator that over here, well, then we're going to get a consistent estimator of our regression quantile coefficients. So that's great. We can still rewrite this a bit. What we can do is that we can again realize that this looks a little bit ugly. We have here, say, yi larger or equal to xib. What we can do is that we can sum over two different summations. First of all, for all those observations for which yi is larger than xib, and we can sum over all those observations for which it's the case that yi is smaller than xib. Then we get this relationship that we have now over here. Well, this beta hat that we have over here, that it's still a little bit difficult to calculate this, and the reason behind that is because of the fact that we have these say absolute values that we have over here. So therefore standard methods such as for example Newton-Raphson methods or quasi-Newton methods such as BFGS, which are going to use the say first order derivative and eventually even the second order derivative. Well, these methods don't work so well, and the reason behind that is because of the fact that these this function that we have over here is not always differentiable. It is differentiable in many places, but not always. So therefore that usually doesn't work so well at the moment that we are going to use methods that are going to assume that we have, say, not the first order derivative only in one particular place, but we actually have it everywhere, such as, for example, BFGS. So therefore, it doesn't usually work to use the, say, standard minimization algorithms over here, but what we can do is that we can write this thing that we have over here as a so-called linear programming technique. We can write this as a linear programming model and then use linear programming techniques in order to solve it. There is a very standard method in order to solve linear programming problems, and that is the simplex method. But, well, even though this has been used in the, say, very first years with respect to quantum regression, it doesn't work so well here. So therefore, in the late 90s, Portnow and Krunker came with, say, an alternative, and they developed a fixed point method based on simulation methods. And that's exactly the way in which, for example, R and Stata are doing this. So, well, there is actually code in Stata. I'm not sure whether it's the say, source of that is available as it's written over here, but at least in Stata you can do this. I'm pretty sure that you can do this in R as well, and in Python you can do this as well. In some other more difficult programming languages, it's not directly available, but still it's not really recommendable to do it yourself, to program it yourself. So even though you could of course read this article that we have over here and to program it yourself, but that's not really necessary, apart from the fact that even in C and C++, well, there is code available. You should also realize that doing it yourself doesn't help you that much more. It's not going to give you any more insights of how this, say, quantum regression actually works. At most, it's going to give you more insight in the, say, programming language that you're using. But apart from that, I don't see any reason to program it yourself. Okay, I would like to now go on with the next topic, and that's the topic of the derivation of the asymptotic distribution of the quantum regression estimator. We should realize that this could have been quite difficult, but it is actually not going to be that difficult, taking into account that most of the things we have already done when we were looking at the standard quantiles. So when we were deriving the asymptotic distribution of standard quantiles, then we already did most of the work that we are going to do right now. So therefore, even though things look a lot harder than what we had over there, you should take into account that essentially we're doing always exactly the same. So therefore what I am going to do first, by the way, is that I'm going to introduce this m function that we have over here. We had that function when we were looking at standard quantiles, but I have never introduced it so far with respect to conditional quantiles. But it's exactly the same idea. Now it's a function of y, x, and b instead of y and q. It's going to be this function that we have now over here. It's exactly the same thing as what we had before with respect to standard quantiles. And then the reason why we're going to do this is because of the fact that then we can see the quantum regression estimator actually nothing else as the argument that's going to minimize this criterion function that we have over here. It's just a notation because of the fact that this we have already seen a couple of slides back. So this works well, and then the next thing we can do is that we can do exactly the same thing as what we did with respect to standard quantiles. First thing is that we're going to look at the first order condition. So even though this m function is not always differentiable, that doesn't mean that we cannot look at the first order condition because of the fact that it's, well, generally, of course, it is differentiable because of the fact that only in the case that, of course, y and x times b are exactly identical to each other, then we have problems. But that doesn't mean that we generally have problems for any x, y, and b. So therefore, we can take here first order derivatives. And that's essentially what I've done over here. Implicitly, of course, with respect to this m function that we have over here. And we have written down the first order condition because of the fact that I have set this simply equal to 0. Another thing that we should take into account here is that I have already multiplied here the left and the right hand side by the square root of n. So therefore, that's the reason why I don't divide here by n, but I divide here by the square root of n. Then the next thing I can do is that I can look now at a Taylor series expansion. And also here what I'm going to do is I'm going to have a Taylor series expansion around the true value of beta tau, and that I will just denote by beta tau itself. I could of course have used here a beta 0 tau or something like that, but I didn't like that much, so I just have here beta tau, which is already the true value. So that means that in the Taylor series expansion, what we're going to get as first is, well, just this function itself, but now no longer evaluated in beta hat, but in beta tau itself. So therefore, we are going to get this as our, say, first part, and then the second part, or the second term that we're going to have. Well, in a Taylor series expansion, that's always the first order derivative. Of course, the first order derivative of this thing that we have over here, but that is already a first order derivative, so therefore it's going to be a second order derivative. So this thing that we have over here, again, not evaluated in beta hat, but of course in beta tau. And then we multiply this always by the difference from where we are going to evaluate our function, that's of course in beta hat, minus where we approximate it, that is in beta, so therefore we get this difference between beta hat tau and beta tau. So that's a thing that we, well, there is nothing special about this thing that we have so far. Also the final term is not that different from what we have already seen so far. We're going to get this rest or order term, again that's going to be equal to OP1 multiplied by the highest order term that we've over here, that's of course equal to beta hat tau minus beta tau once again, and that is now going to be equal to 0. It's equal to 0 simply because of the fact that, well, this thing that we have over here is equal to 0, and we should realize that, as what we have seen with respect to standard quantiles, this thing that we have here at the left hand side is equal to these three terms that we have here at the left hand side. And the reason behind that is because of the fact that this order term makes actually these two things here at the left hand side and that thing that there at the left hand side, it makes it equal. Because of the fact that these first two terms, they are just an approximation of course, but the definition of the order term is that that's actually the difference between the approximation and this term that we have over here. So therefore, these three terms over here should be equal to that term that we have over there. That one is equal to 0, so also this is equal to 0. Then the next thing I'm going to do is that I'm going to multiply now the first term by the square root of n divided by the square root of n. I'm going to do that. Then we get here just an n, we divide by n then. And I can take this square root of n, I can take it there. And then again, you should immediately recognize that this is very nice, because now what we have is the square root of n multiplied by beta hat tau minus beta tau. I actually want to have the asymptotic distribution, of course, of this term that we have over here. So how are we going to get that? Well, the first thing I can do is that I can try to single out this. So get this at the left hand side and everything else at the right hand side. I can do that first of all by, well, bringing this of course to the right hand side, this term that's over here. Also this term can be brought to the right hand side in order to get this thing over here. Of course, now we have a minus sign here in front, not here because of the fact that plus or minus OP1 is exactly the same. And then what I can do is that I can divide then the left and the right hand side by this term that we have over here. So then what we're going to get in the end is this equation that we have over here, where we have now at the left hand side exactly what we wanted. This is where we want to get our asymptotic distribution of. And the right hand side we have, well, two terms. This term, this is quite difficult, and this remaining order term that we have over here. I'm going not to say anything about this order term because of the fact that that very quickly goes to 0. Well, this order term itself, by definition, goes to 0 if n goes to infinity. But we should also take into account that this also goes to 0 in probability because of the fact that we do know that beta hat tau is a consistent estimator of beta tau, so therefore it's going to converge to beta tau. So this whole thing is going to go to 0. So therefore the only thing that I really have to focus upon is, well, are these terms that we have over here. Well, what I'm going to do again is that I'm going to focus first on the numerator. Again, what I can do is that I can multiply now the numerator by the square root of n divided by the square root of n. Then these two square root of n's, they just become n together, so we get 1 over n. And we still have then the square root of n here in front. And then what we should realize is that for this we again use the central limit theorem. Again, it's a sample mean multiplied by the square root of n, so therefore we can use the central limit theorem for that. And that means, of course, that this is going to converge, well, in probability, to a normal distribution with a mean equal to the corresponding population mean. What is that? Well, again, that is no summation, but expectation. We're not going to sum over all the observations, but just the first one, we get rid of the 1 over n that we have over here in order to get this here at the left-hand side. And actually here, you should realize again that this is the left-hand side of a first-order condition. Oh, you have to scroll back a little bit because of the fact that it was actually over here. Well, you could say over here. We should realize that what we have over here, or maybe better to say over here, is exactly the minimization of our m function. And that means, of course, that if we would then like to look at the minimum of this m function that we have over here, well, then what we're going to get is exactly that thing that we had over there. So therefore, what we are doing here is that we have here the left-hand side of the first order condition of the minimization problem. Of course, the right-hand side is always equal to 0, so that means, of course, that this left-hand side should be also equal to 0. So therefore, for the normal distribution, we do know that the mean is now going to be equal to 0. What about the variance? Well, what we do know is that the variance is always going to be equal to the population variance. That's essentially exactly equal to this thing that we have here at the left-hand side, but then we get something like a variance of this thing that we have over here. But that's by definition always equal to the second moment minus the first moment squared. Well, we do know now that the first moment is, of course, this thing over here. That's equal to 0. So therefore, the only thing that we really have to focus on is the second moment, which is actually exactly the same thing as what we have over here. But the only thing we need to do is to square that term that we have here within the parentheses. So therefore, then we're going to get this thing that we have over here. Well, then, of course, what I would like to do now is that I would like to calculate this thing over here. But again, it's going to be quite hard to directly calculate this. So therefore, the first thing I'm going to do is that I'm going to just look at the thing here that we have here within parentheses, this first order derivative. What is that first order derivative? Well, that's of course the first order derivative of our m function, and we just defined it to be equal to this thing over here. Well, again, we should realize that generally it's hard to say first to take the first order derivative of this thing over here, but again, we should realize that, well, here, this thing, at least for the first order derivative, is only different from 0 at the moment that y is larger than x times b. So that means that the absolute values of y minus x times b should be essentially this thing should be positive, so therefore the absolute value should be exactly the same as this thing that we have over here, but then without, say, absolute values. Here's the other way around. Here y is smaller than x times b, so that means of course that y minus x times b is negative, so therefore in absolute values y minus x times b is equal to xb minus y, so therefore we can even write it like this thing that we now have over here. So now what we can do is that now it's no longer that difficult to take first order derivatives. We have here a constant. Well, I said before that we take this thing over here also as a constant. That's not completely true, of course, but well, don't bother too much about that. And then we can take the first order derivative of this thing that we have over here with respect to b. What is that? Well, that's of course equal to minus x. Now, an important question arises: is this actually a vector? Is this a vector, and should we write then x transpose, or should we just write x or something like that? I always find that really difficult. So therefore, what I'm going to do over here is that I'm just going to assume that this thing that we have over here is just one-dimensional. And that's what I usually do. At the moment that I get more difficult things, like well, deriving this asymptotic distribution that we have over here, I typically myself, I'm just going to assume that this thing that we have over here is one-dimensional. Reason behind that is because of the fact that then I can actually focus on the difficult parts and not that much on things which I think are a little bit boring, and that is the, say, linear algebra behind it. Maybe that sounds maybe a little bit surprising, but well, during your econometrics lecture series, of course, you have had some linear algebra before, and maybe you got the impression that especially we econometricians like linear algebra and models with linear algebra a lot. Well, I have to say, not me. I have to say that I do not really like it that much. The main reason is because of the fact that it's so difficult to understand it. So therefore, I just here assume that x is just one-dimensional. Of course, later on we can always look at how that actually extends to the more dimensional case. But what we need, of course, is that we are going to condition on something, and that is this thing over here. Well, then for this part over here, we get 1 minus tau multiplied by that. And now we actually get simply an x. So therefore, in total, what we're going to get now are all these terms that we have over here. So now what we can do is that we can square them. So I can square this term, I can square that term. Then we get, of course, tau squared multiplied by this thing over here squared, but that's not really necessary to square, of course. But this thing we have to square, so we get x squared there. And here we also get an x squared, 1 minus tau squared, and this thing I don't have to square. Of course, again, the cross term, 2 times this thing multiplied by that thing, again, is going to be equal to 0. So therefore, in the end, we're going to get this thing that we have over here. And now what I finally have to do is that I have to take the mean of this thing over here. But take into account that what I need to do, in fact, is take the mean with respect to y1 next one. That I find myself quite difficult, especially since we now have this x1 in here. So therefore what I'm going to do first is that I'm going to look at the mean of y1 conditional on x1. So assuming that x1 is something which is completely deterministic, that it is already known to us, and then we can integrate, well, with respect to the x1s using the law of iterated expectations. So that's what I'm going to do over here. So we're going to look at the mean, the thing that we just have derived, conditional x1 equal to x. That's of course nothing else as the integral over the, well, conditional support that we have over here, of this thing over here, and then multiplied by this density function that we have over there. So that again looks all quite nice. Then what we can do is that we can then simply substitute in the thing that we had the previous slide. So this is what we had at the previous slide. Well, then again, what I can do is that I can bring in this density function in parentheses. So then we get the density function over here, but also, of course, here. Now we have even longer parentheses, but we should realize that we now have an integral over a sum. That's, of course, nothing else as a sum of integrals. So therefore, we can also write this essentially as these two integrals that we have over here, where I have already taken out the tau squared and the 1 minus tau squared. Again, I can do something with respect to the integration or the area of integration, even though we do integrate here over the full support of y conditional x. We should realize that we can also integrate over, well, we can integrate from x beta tau until the supremum of y conditional x, because of the fact that we have here the indicator function that y must be larger than x times beta tau. And then in addition to that, we can do exactly the same ID over here, but then of course we're going to integrate from the infimum of y conditional x up till x times beta tau. So if we're going to do that, then we get this thing now that we have over here. And then, well, finally what we can do is that we can now integrate this thing that we have over here. We have here a density function, so the primitive density function is by definition a distribution function, and we have exactly the same over there. So then what we're going to get is now well, first of all, we have to evaluate this thing in the supremum. That's of course equal to 1 minus this thing evaluating x beta tau. And then what we have over here is that we another time are going to evaluate it in x beta tau minus, of course, this thing evaluating infimum, but that is simply equal to 0. So therefore, in total, what we're going to get is now this thing that we have over here. Again, we could realize that this thing that we have over here is actually equal to tau, and the reason behind that is because of the fact that it's the conditional distribution of y1 conditional x1 actually evaluated in the conditional quanta. So therefore this thing over here is just equal to tau, and that actually also holds true for that thing that we have over there. Then what we can do is that we can well, take the x squared, we can take them out, but at the same time we can also take the tau out here. We have a tau there and we have a tau squared there. So therefore what we're going to get now is tau multiplied by 1 minus tau plus 1 minus tau squared. And also here we can take first of all a 1 minus tau out. We have also then in the standard quantiles, and then in total what we're going to get here in parentheses is tau plus 1 minus tau. The tau and the 1 minus tau, they are going to cancel, of course. So in the end, the only thing that we're going to be left with is tau multiplied by 1 minus tau squared. Well, and then we should realize that, well, we were not really interested in this thing over here, but instead, as I already said, we're interested in the mean of y1 and x1, so the joint mean of y1 and x1, and actually not on this conditional mean over there. But as I already said, what we can do is that we can use the, well, law of iterated expectation, integrating over the full support of the x's, and then getting this conditional mean that over here, multiplied by the density of x1, and then of course multiplied by this dx that we have over there. Then the only thing that I need to do is to substitute this into there, so we get it then of course there tau 1 minus tau x squared. I can already take the tau multiplied by 1 minus tau, I can take it out, and then we have this thing over here. Take also here into account that this is actually nothing else as a population mean. It's again a population mean because we have here an integral over the full support of x, and we have here the density of x, x1. So therefore this is actually nothing else as the second moment of x1. So this is nothing else as the mean of x1 squared. So therefore now what we have is this thing we have over here. Now we should realize that we can recap a little bit. The question of course arises, what have we been doing in the last 5 minutes? Well, remember that what we wanted to do is that we wanted to look at the asymptotic distribution of this term that we have over here. But so far we have only been focusing on the numerator, and now we know that the numerator is going to converge in distribution to a normal distribution with a mean equal to 0 and a variance equal to tau multiplied by 1 minus tau multiplied by the second moment of x. However, what about the denominator? Well, with respect to the denominator, we should realize that this is actually somewhat simpler, and the reason behind that is because of the fact that we divide by n instead of the square root of n that we had over there, and that means that by the law of large numbers, this denominator simply is going to converge in probability. Well, this is a sample mean, so therefore it's going to converge to its corresponding population mean. So that means that in order to find the corresponding population mean, we should not have summation but expectation. We're not going to sum over all the observations that we have, but only the first observation. And we no longer divide by n in order to get actually the thing that we have, well, a little bit further. We actually have that over here. We should realize that the denominator we have just looked at is going to converge to this term that we have over here. However, also here the question arises, what is this term that we have over here? In order to know that a little bit better, what we could do is that we have here the mean of the second order derivative of this m function that we have over here. What we could of course do is first of all ask ourselves the question, how does this m function look like? And then take the first and the second order derivative sequentially. However, here I'm going to use the same steps as what I had done with respect to the variance of the numerator, and that is that I'm going to first of all look at the conditional mean, not the joint mean directly, take into account that this again is a joint mean. But what I'm going to do is that I'm going to look at the conditional mean, the mean of y1 conditional on x1, and then first thing that we're going to do is that we're just going to look at the m function itself. What is this thing that we have over here? Well, this is of course nothing else as an integral now on the conditional support of y conditional on x, and of course we get here the conditional density. Then what we can do is that we can substitute in the m function, then we get now this thing that we have over here, and now we're going to take a couple of steps that should look familiar to you. The first step that I'm going to do is that I'm going to bring in the density function here within the parentheses. So I'm going to multiply it here and there in order now to get this very long parenthesis, very long integral that we have now over here. Then in addition to that, another step that we can take is that we can now realize that we have now two different integrals, one over here and one over there. So we can then write it like that. And also the next step that we're going to take is comparable to what we have seen before, and that is that instead of integrating over the full support over here, I'm only going to integrate from xb up till the supremum of y conditional on x. And here I do the other way around. Here I'm only going to integrate from the infimum of y conditional on x up till xb. So therefore, now we're going to get this thing that we have over here. Then another thing that we can do, that's not what we have just done, but we have already done that also before. But then when we, were looking at the quantiles themselves, is that we now should realize that even though we have here absolute numbers, we should realize that we only integrate with respect to y from values from x, b, and above. And that means, of course, that the y that we have over here is always larger than x times b, which means that y minus x times b is always going to be positive. And that means that y minus x by xb in absolute values is simply y minus x times b. So therefore, we can simply write this as y minus x times b. We can also look at this thing that we have over here. Well, here we should realize that's the other way around. Here, the values of y that we have over here are always smaller as x times b. So therefore, y minus x times b is equal to xb minus y. So therefore, we can write it like all these terms that we have over here. Then we can do also a thing that we have already seen before, but then with respect to the quantiles, and that is that we can now use partial integration. Well, remember from the quantiles, when we were looking at partial integration, that even though we can look here at the primitive of this density function that we have over here, which is of course the distribution function, we can also use minus 1 minus the distribution function. And that's what I'm going to do here as well. So we get minus 1 minus this distribution function, of course, multiplied by y minus kb, or kx times b, and then of course evaluating these two values that we have over here in order to get this term that we have over here. Well, then in addition to that, we then have to, we get minus, but we have here a minus sign in front, so there we get a plus over here. And then what we're going to get is that we are going to get the first order derivative of this thing over here with respect to y. That's simply equal to 1. So therefore, in the end, we're going to get this integral over here because of the fact that we still have this 1 minus the distribution function over here. Then we can also look at the second term. Well, with respect to the second term, I'm simply going to use the distribution function as being the primitive of this density function that we have over here. So there we get the distribution function multiplied, of course, by xb minus y, and then, of course, evaluating these two terms over here. So then we get this term over here. And then what we're going to get is another time a minus, but we should realize that we have to multiply that by the first order derivative x times b minus y with respect to y, so that gives us another time a minus. So therefore, again, we get a plus over here, well, plus 1 minus tau from this 1 minus tau that is over there. And then we're going to get just the, well, distribution function. So therefore, we have the distribution function over here. So again, this is quite like what we have seen before with respect to, say, the standard quantiles. And then we should also here realize that this term as well as that term, they're equal to 0. We see that directly because of the fact that, for example, at the moment that we're going to evaluate this term in the supremum, well, that will give us a 1. So we get 1 minus 1 is equal to 0. At the moment that we're going to evaluate, well, this whole term in x times b, then we see here over here that we get xb minus xb. Also, that is equal to 0. So this whole term over here is going to be equal to 0. Well, the same is true for this term over here. First of all, xb minus xb is equal to 0. And also this term over here is equal to 0 because of the fact that we have to evaluate it here in the infimum of y conditional max. So therefore, this term and that term, they are equal to 0. So the final thing that we only have are these two terms that we have over here. And then what we need to do is that we have to take the first order derivative. Well, officially what we need to do is that we have to take the mean of the first order derivative. So I have to take here the, well, first order derivative here within the mean. That's going to be difficult with respect to this equation that we have over here, but we do already know under very general conditions, it's always the case that the mean of the first order derivative is the first order derivative of the mean. So there we can just take the first order derivative of this thing that we have over here. Here again we are going to use Leibniz rule, and that means, of course, that what we're going to get is, well, first of all, we are going to take the first order derivative of this term over here. Well, according to Leibniz rule, this actually doesn't depend at all on b, so we don't have to take that into account. Also, the supremum doesn't depend on b, but the lower bound that we have over here does depend on b. So what we're going to get in total is tau times, well, x times this thing, but evaluating x times b. So these are all these terms that we have over here. And then, in addition to that, we are going to get this term that is over here. And then what we're going to get here is 1 minus tau, of course. Well, again, this, well, first order derivative with respect to b doesn't give us anything. But for the upper bound, we, of course, are going to have first order derivative equal again to x, and then multiplied by this thing that over here, evaluating x times b. So in total, we are going to get all these terms that we have over here. We have here a minus sign in front because of the fact that this was actually with respect to the lower bound. So therefore, we are going to get all these terms over here. Well, the first thing that we can actually now do is that we can now get rid of the parentheses. So we get then a minus tau over here. We get plus tau times this thing over here. Well, of course, everything multiplied by x. And here we are going to get minus the distribution function evaluated or multiplied by x. And then here we get minus tau times the distribution function times x again. So in total, we're going to get all these things over here. It's now immediately clear that this term and that term, they are going to cancel to each other. So therefore, in the end, we're only going to get these two terms that we have over here. Well, now we are not interested in the first order derivative, but we are actually interested in the second order derivative. Again, we should realize that the mean of the second order derivative that's actually the thing that we're interested in, is equal to the, say, second order derivative of the mean. And we already know what the first order derivative is, so the only thing we need actually to do is to take the first order derivative of this thing over here. Well, that's now not that difficult anymore. This doesn't depend on b at all, but this does. What we are going to get is the, well, density function, of course, no longer the distribution function, but the density function evaluating x times b, multiplied by the first order derivative of xb with respect to b. That gives us an x, but we already had an x over there, so therefore in the end we are going to get an x squared. So therefore in the end we're going to get this thing over here, but we should realize that what we really wanted was not the, say, conditional mean, but we actually want the joint mean of x and y. And now we have conditioned on a particular level of x, this x, and those x's that we have over there. But again, we can use the law of iterated expectation in order to get the joint mean. This is now the joint mean, and what we're going to get is that we are going to integrate over the possible outcomes with respect to x, so the full support of x, and now of the mean, this mean over here, conditional on x1 equal to x, and then multiplied, of course, by the density function of x1, assuming at least here that x1 is going to be continuous. That's not really necessary, but otherwise we would have gotten here a little bit of different notation. So therefore we are going to get now this over here. What we can do is that we can substitute this into there in order now to get this relationship that we now have over here. Well, again, we should realize that this again is actually a population mean. It's again an integral over the full support of x, and we actually have here the density of x as well. So therefore, there's actually nothing else as a mean with respect to x1 that we have over here. So therefore, we can also write this, in fact, nothing else as this mean that we have now over here. We have replaced the small x's over there by a large x, x1 as we have it over here. So that implies that now we are actually done, because now we could realize that, well, going back once more to this slide that we have now over here, this slide that we have over here, we should realize that once again, well, we wanted the asymptotic distribution of this thing that we have over here. Now we do know that the, say, numerator is going to go to a normal distribution with a mean equal to 0 and a variance as we have earlier derived. And now we also know that the denominator is going to converge in probability to just that mean that we have just derived. And that means that the numerator divided by the denominator is also going to converge to a normal distribution, again with a mean equal to 0 and a variance equal to, well, where the, say, variance of the numerator is going to converge to, divided by where the denominator was going to converge to, but squared, of course. So therefore, in total, what we're going to get is, well, I have to now another time go forward. What we are going to get in the end is that our variance is going to be equal to this thing over here. This is for the numerator, and this is for the denominator, but we have to, of course, square it. Well, now we should realize that, again, this thing over here, well, even though it looks very simple, we don't know it. And the reason behind that is, for example, that we do not know the beta tau. And we also do not know these, say, means that we have over here. The most difficult of all, you could actually say, is the denominator. This thing that we have here within the square in the denominator, that one is the most difficult. So the question arises, how could we actually estimate? Well, we should again realize that that term, that's this term over here, again is a, it's a population mean. So therefore it can be estimated by its corresponding sample mean. That means again, no expectation, but summation. We're going to sum over all the observation, we divide by n. But we should realize, of course, that we do not know what beta tau is. So we replace it by an estimator of beta tau, essentially the quantile regression estimator. And we also do not know this density, so therefore we are going to replace that also by an estimator. But the main question then, of course, arises, well, how are we going to estimate that thing there? We can estimate that by a so-called kernel estimator. We have here a kernel function. And then what we're going to do is that we're simply going to evaluate that in this term over here, where, of course, this is going to be the bandwidth of our kernel function. This, unfortunately, is based on the choice of the kernel and the bandwidth, but we cannot do too much about it and take into account that, well, standard statistical packages actually use this method. I have to say one thing more, and that is, of course, about this mean that we over here. Well, that's relatively simple. This is, of course, a population mean with respect to the second moment. Well, we can actually use the sample mean for that again instead. As I already said, Stata, but also R uses this method to calculate the standard errors. Okay, I would like to go on, and I would like to go on with an, well, empirical example, and that's actually based on research by myself. That's a paper that I published in 2009 in Labor Economics, and that was worked together with Jim Albert and Susan Froman, both from Georgetown University. The idea is that what we're going to do is that we're going to look here at quantile regressions. Well, we did in this paper itself, we did much more than that, but we also looked at quantile regression over there, and what we do there is that we look only at full-time working women in the Netherlands. So we look at the wages of these full-time working women in the Netherlands. The data set that we use is the OSA Labor Supply Panel Survey. That's actually a survey that you can even use up till today. It's a biannual survey. It started actually to be annually, but now it's biannually, and it started in the mid-80s with around 4,000 individuals that were at that time representative for the labor market. Well, actually the people that started in the 1980s, in the mid-1980s, are quite old now. Probably they're not working anymore. But, well, there is some replacement. So most of the people that are now in this sample or in the panel probably didn't start in the panel in the mid-80s. What I'm going to do is that I could have, of course, looked at many different waves, but I'm going to look here at the wave of 1992. That's also what we did in this paper that we have over here. Now you should realize, of course, that this paper is already quite old, 2009, but it was not as old as the data that we were using. The reason why we used this data was because of the fact that it was a little bit richer than all of the other waves that were at that time available. So that was the main reason. Let's look at the results. What we are going to look at over here is that we're going to look at median regression, so 50%. Here is median regression. And we're going to look here at, I would say, first quintile and last quintile regression. And, well, even though I have included many more things here with respect to the log hourly wage, so log hourly wage is the left-hand side variable, you should realize that the main thing that we're going to focus upon here is the years of experience, and we are going to look here at the impact of education. We can conclude a couple of things from this. First of all, at the moment we're going to look at the constant. Well, the constant usually doesn't have a very large interpretation, like you usually also have at the moment that you're going to look at standard linear regression analysis. There also, people usually don't give the constant a lot of interpretation, but you should take one thing into account, and that is that we see that the constant actually increases along the distribution. That is not that strange. And the reason behind that is because of the fact that the conditional quantiles have to increase along the distribution, and therefore, well, since the constant actually determines for a large extent the conditional quantiles, that's also the reason why this is increasing over the distribution. In addition to that, we can also look at the years of experience. There we do see that it's, well, it is positive, and it's actually also quite large. We do actually see that it's also increasing with respect to the distribution. So individuals at the top of the distribution, or women at the top of the distribution, do have a larger impact with respect to additional years of experience compared to those at the bottom of the distribution. But again, this could, of course, simply be related to the fact that these persons have higher wages, of course, in general. Then we could also look at education. Well, here we have three different levels of education: lower secondary, upper secondary, and a bachelor's or master's degree. Very rough, of course, but what we're going to see is that, well, first of all, we do see that there is a return to education. Not that sure whether it's so large. For bachelor and master, we see that it's about 30% higher than at the moment that you even do not have a lower secondary education. We do not see so much of an impact here with respect to whether you're higher up in the distribution, at least for this one and this one are exactly identical to each other. This one is a little bit higher, but we should take into account that, well, given the standard error that we have over here, the difference here might actually not be significant at all. Okay, I would like to go on with the next topic, and that's the topic of distribution regression. If you look at the title of my slides at the beginning, then you should realize that what I say is that I'm going to do something with respect to both quantile and distribution regression. However, I haven't done anything yet with respect to distribution regression, and that's going to change right now because of the fact that now I'm going to say that there is an alternative to quantile regression that we have discussed so far, and that is distribution regression. In order to introduce distribution regression and to answer the question, what is actually distribution regression? Well, we can be very short. What we can say is that when we looked at quantile regression, then quantile regression was actually nothing else as a method in order to look at conditional quantiles, essentially to estimate conditional quantiles. That is different from standard regression because of the fact that in standard regression you try to estimate conditional means. So therefore it doesn't come as a big surprise that at the moment we're going to look at distribution regression, that I now say that distribution regression tries to estimate conditional distributions. So that is exactly what distribution regression does. We will say a bit more about this, well, after the next slide. But before I'm going to do that, I would want to say something about the, what you could say, benefits and drawbacks with respect to quantile and distribution regression. This is more about the fact that at the moment that we're going to look at these two methods, then you might get the impression that maybe one of the methods is better than the other. That's not completely true. It is the case that in some situations quantile regression could be the better method to use. However, in other situations it could be the other way around. It could be the case that it would be better to use distribution regression rather than quantile regression. So therefore the good thing is to look at the benefits and the drawbacks with respect to both the quantile regression and distribution regression. Well, what I'm actually going to do is I'm going to look here at the benefits and the drawbacks with respect to the distribution regression only. And what we can say is that the benefits for distribution regressions are the drawbacks for quantile regression, and of course the other way around. At the moment that I discuss the drawbacks of distribution regression, then these are of course the benefits of quantile regression. So let's start with the benefits of distribution regression. Well, the first thing is that distribution regression is much simpler and it's faster than quantile regression. What we should take into account is that we have now looked so far at quantile regression, and I hope that you at least got the impression that doing quantile regression generally is much more difficult than at the moment that we're going to look at standard linear regression. And this becomes even more important at the moment that we're going to look at special cases that we will later on do during this lecture series. So therefore generally quantile regression is more difficult, but you should also take into account that it's also extremely complex, not just for us to understand it, but also for, say, computers. Nowadays, of course, computers are pretty fast, and therefore you can, well, for a reasonable data set, say 10,000 observations, or even more, and for a reasonable number of regressors, we can actually do quantile regression these days. But take into account that, well, unlike what you, of course, can do with standard regression analysis, don't try to do quantile regression on, say, a couple of millions of observations and, say, a couple of thousands of different regressors. Then, well, that would be possible to do in general these days with respect to standard regression analysis, but I wouldn't advise you to do that with respect to quantile regression. Most likely, you won't get any answer, or at least you won't get any answer before before a couple of 100 years. So therefore you should realize that doesn't really work. Distribution regression still is more difficult than standard quantile regression, but we do find that, well, distribution regression generally is simpler and also faster. It's just, you could say, probit analysis, and that is much faster than what we have seen so far with respect to quantile regression. So that's the first benefit. The second benefit is that sometimes one wants to estimate a distribution rather than a quantile. We'll get to a particular example with respect to the next topic, where we're going to look at counterfactual distributions. If you want to estimate a distribution, then you may, of course, say you could use quantile regression with respect to that, because quantile regression, quantiles are, of course, well, nothing else as, well, inverse distribution functions, and quantile regression tries to estimate, of course, quantiles. So therefore, we should realize that at the moment that we're going to do quantile regression, we get inverse distribution functions, and therefore we can invert those inverse distribution functions in order to get the distribution function themselves. So essentially it is possible to estimate distributions based on quantile regression. However, especially taking this thing into account, that it's actually quite complex, quantile regression, it doesn't make that much sense to first, well, invert the distribution function and then invert it backwards in order to get the distribution itself. In that sense, it would be much better to immediately look for a method that can directly estimate the distribution function, or at least the conditional distribution function. Then the final benefit with respect to distribution regression is that it can be easily used when the outcome variable is discrete. Actually, you don't even have to do anything at the moment that the outcome variable is discrete, at the moment that you have distribution regression. And that's actually not true at the moment that we're going to look at quantile regression. Later on, we will look at situations in which the outcome variable may be discrete in quantile regression, but we will see that that is actually quite complex. So these are the, say, benefits of distribution regression, and in that sense also the, well, drawbacks with respect to quantile regression. But what about the drawbacks with respect to distribution regression? Well, you can say that there's actually only one important drawback with respect to distribution regression. That's a very important one, and that's the interpretation. In general, it's much easier to think in terms of quantiles than in terms of distributions. Let's look at a very simple example. Suppose that once again we are going to look at log hourly wages, and we would like to look at the impact of particular things on the log hourly wage, such as, for example, a college degree. At the moment that we're going to look at quantile regressions, well, we have just done that in the previous example. Then, for example, at the moment that we're going to see that a college degree has a, say, beta coefficient equal to, say, for example, 0.3 or 0.4, that means then that at that particular quantile, for example, the median, at the moment that somebody is going to have a college degree, that person is going to get, well, respectively 30 or 40% more in terms of the log hourly wage in terms of that particular median. So the median is going to increase by, say, 30 or 40%, depending, of course, on what the beta coefficient is going to be. That's relatively easy to understand, and that's quite comparable to the situation that we have with respect to the mean or mean regressions standard regressions in which we can actually say that a 0.3 or a 0.4 actually says that the mean or the conditional mean is going to increase by that amount at the moment that someone is going to have a college degree. But in terms of distribution regression, it's going to be more difficult. The moment that we're going to look at distribution regression, we're going to look at probabilities. So then at the moment that we would like to look at the impact of, say, a college degree, then we are going to look at how the probability is going to change, the probability that you earn less than a certain amount, say for example 5,000 euros a month, at the moment that you're going to have a college degree. Well, this impact of course is negative. We can expect that individuals with a college degree are going to have higher wages, so therefore the probability that they will earn less per month than say 5,000 euros, that of course is going to be negative because they have a higher likelihood to actually earn more than 5,000 euros. But in general, it's much more difficult to interpret, say, probabilities than at the moment that we're going to simply look at quantiles such as medians, first and third quartiles. So that's the main reason why distribution regression is not always used. But now let's look at the idea behind distribution regression. The main idea behind distribution regression is extremely simple. We should realize that at the moment that we have a particular random variable y, then of course that random variable always has a distribution function that we denote by this f subscript y that is over here and evaluated in this little y that is over there. Now we should realize that it's always possible to write this in another form. We can always write this as phi, where phi is now going to be the standard normal distribution function. So the distribution function that looks like this well, famous form that you actually have, that you actually know about. And in addition to that, we have here that distribution function, that standard normal distribution function, is evaluated now not in y, but in another function, mu y that is over here. And mu is now a uniquely determined function. This looks like a really big thing, that it is possible to write any kind of, say, for any kind of random variable, the distribution function, in this form that we've over here. We are going to now no longer evaluate our random variable in our distribution function, but actually in a standard normal distribution function. This means, by the way, that if we are going to look at the random variable mu, capital Y, that is standard normally distributed. So this looks like a really big thing, but you should take into account that this is actually something which is completely trivial. The reason behind that, because of the fact that first of all we should realize that both this distribution function as well as this normal distribution function, they're upward sloping, and they can only take values in between 0 and 1. Their range is always in between 0 and 1. And therefore, if we are going to look at this relationship that is over here, it's always possible to take the inverse from the standard normal distribution from the left and the right hand side. And then we immediately see that the unique solution of this mu that we have over here is simply equal to the inverse, well, standard normal distribution function evaluating this thing that we've over here. And take into account that for any y that we have over here, we can actually do this. And we should also take into account that this thing over here is always in between 0 and 1. And that's great because of the fact that we should also take into account that this inverse distribution function can only take values in between 0 and 1. But we immediately see that the statement that we made over there is actually quite trivial, just based on the fact that this thing is invertible. But we can also do this with respect to conditional distribution. So we should also take into account that if this is true, then it's also true with respect to the conditional distribution. So we can also write the conditional distribution on y conditional on x, well, as the standard normal distribution function, but now evaluated in a function mu, which is now not only a function of y, but also on x, on the different values of x that we have over here. Also here we should take into account that this is completely trivial. Now I just did this conditional on the x that we have over there. So that means, of course, that we could actually do this for any kind of random variable y conditional on x, in the same way as what we had over there, but we should take into account that we would only know how this function mu looks like at the moment that we do know how this conditional distribution over here is going to look like. And this is of course related to the data distribution, as we say as econometricians. And we should take into account that usually, as for us as econometricians, this distribution is unknown for us. So therefore, what we can do at most is try to estimate this mu function that we have over here. So take into account that if we would have known this distribution function over here, then we can simply, well, calculate mu based on the idea that we had the previous slide, but that is impossible for us. We can try to estimate, at least for a particular, say, x that we have over here. Suppose that x is discretely distributed. Then what we can do is that we can estimate this mu hat for that particular x and a particular y by using something which is quite related to standard probability. What we could do is that we could first of all only look at those observations for which xi is exactly equal to x. So of course, if we're going to look at the total data set that we have, there could be a lot of observations for which xi is not equal to x, but we're only going to focus here on those observations for which xi are exactly equal to x. And then based on that, we are going to introduce a dummy variable, which is equal to 1 in the case that yi is smaller or equal to y, and 0 otherwise. So therefore, at the moment that we are going to have an observation for which yi is smaller or equal to y, then we multiply this by the log of this phi m that we have over here. Well, taking into account that this is exactly the same thing as what we typically have in standard probability models, and here we get 1 minus that dummy variable that we have just introduced, multiplied by the logarithm of 1 minus this phi m that we have over here. And then we maximize this function that we have over here with respect to m, and we get that thing that we have then over there. We should, by the way, realize that this, even though this looks very fancy, this is actually nothing else as that we probably already have seen before, or at least I have seen it before, and that is that this is actually nothing else as the empirical distribution function of y conditional on x. If you know anything about how actually a probit model works, at the moment that we are not going to introduce any x's, so at the moment that we just have a constant, then you might already know that the outcome in that particular situation is just our normal distribution function, or actually the inverse of a standard normal distribution function, evaluated in, well, it's actually evaluated in the percentage of observations for which we have a 1. So if we have 50% of our observations are equal to 1, for example, then in that particular situation, our, say, only coefficient that we have, of course, the constant, is simply equal to 0. And well, if it's going to be more than 50%, it's going to be positive. Otherwise, it's going to be negative. So generally speaking, what we can do is that we can simply look at the percentage, in this case, only among those observations for which xi is, of course, exactly equal to x. We can look at the percentage of observations for which this actually is true, so for which the dummy variable is equal to 1, and then evaluate that in the inverse distribution function, and we get immediately our mu hat for any y that we might be interested in, and of course also any x that we may be interested in. Take into account that at the moment that we're going to then substitute this back into my distribution function over here, then we only get this thing that we have over here, and you should realize this is actually nothing else as the standard empirical distribution function. It's a step function that makes a step upwards for any observation that we have. So essentially this is not that interesting to do. Apart from that, you should take into account that we generally have a problem as soon as, well, this xi that we have over here is not discrete. If xi is going to be discrete, in the case that xi is going to be continuous, well then the problem that we are going to have is that we will actually have no observation. The likelihood that we have an observation exactly equal to this little x that is over there, that likelihood is simply equal to 0. So that means that we will not have any observation for which xi is exactly equal to x. That means, of course, that if we then are going to look at this outcome over here, then we simply have 0 divided by 0. So then that doesn't work. But even in the case that we have a discrete outcome, but the number of outcomes is actually quite large, or we have just dummies, but we have many of them, well then actually doing this thing over here may not be that, say, efficient. So therefore, it may be a good idea to, well, have some parametrization over here. One thing that we could do is that we could assume that mu ix, so our mu ix function that we do not know, of course, as long as we know the distribution function, let's assume at least that this mu ix can be written as px times beta y, where beta is just a set of coefficients, and here this px is nothing else as a polynomial of our x's. So that could be, if in the case that we just have one x, could be x squared, x to the power 3, x to the power 4, apart from including, of course, a constant. But another thing that we could do is that we could, at the moment that we are going to have more than one x, well, then we can do that for these polynomials, of course, for any kind of x that we have, but we can also use interaction terms, of course, the first x multiplied with the second x and things like that. We can even think of, for example, a piecewise constant function or piecewise linear functions in order to be even more flexible. But what we want to have is here a very flexible specification with respect to the x's, and then just multiply that with respect to the beta y that we have over here. This usually is called a series regression. We might even want to use here, say, machine learning techniques like lasso or something like that in order to find the correct specification of this px that we have over here. But whatever we are going to do, what we could do then in that particular situation is that we are going to use then essentially nothing else as standard probit. We're going to now use this criterion function. We're going to maximize this criterion function with respect to the beta coefficients that we have over here. Take into account that these beta coefficients, just a set of beta coefficients for a given y that we have over there. And as I already said, this is actually nothing else as doing standard probit with a dummy variable that we have over here for, say, y I smaller or equal to 1. This is, of course, equal to 1 minus that dummy variable that we have over there. So this actually can be done simply, essentially in Stata by using probit and to define yourself these dummy variables that we have over here. Well, essentially, at the moment that we're going to use a standard software package such as Stata, then apart from the fact that we get these betas over here, we also are going to get the standard errors with respect to those betas. We'll take into account that these standard errors cannot be used over here. The reason behind that is because of the fact that officially what we're doing here is not to estimate beta coefficients, but take into account that these beta coefficients that we have over here actually are values for a particular function. So what we essentially are doing here is estimating a function rather than simply a coefficient. And that makes standard econometrics well, no longer useful. And for this we need much more difficult econometrics, such as empirical process theory, but that's not going to be discussed over here. Okay, we'd like to go on with the next topic, and that's the topic of counterfactual distributions. In many situations, we would like to compare distributions of, say, different random variables with each other. That's especially interesting at the moment that we have one particular outcome variable, but we are going to look at that outcome variable for different groups. For example, we could look at wages. We could look at log hourly wages, and we could compare the distribution of log hourly wages from that of women. We could compare that with respect to the same distribution, but then for men. More general, what we can do is that we could look at two random variables. We're going to denote them as YA and YB, and we could look at the corresponding distribution functions Fya and Fyb, and it could be possible that we would like to make a comparison between, say, these two distribution functions, because of the fact that we have two random variables could be quite different from each other, and we would like to investigate that difference a little bit further. Again, for example, we could have here that the A group is going to be women and the B group could be men. We are going to allow for the fact that this random variable ya, and of course the distribution function of that random variable ya, is going to be affected by, say, a set of regressors. Typically we call them characteristics, and I'm going to denote this by xa. So xa could be multidimensional, could be all kinds of characteristics or regressors that are going to have an impact on this random variable ya that we have over there. The same way you're going to do with respect to yb, we are going to have a set of characteristics that we are going to denote by xb that are going to have an impact on this, say, random variable, hence its distribution function that we have over there. Well, then at the moment that we're going to compare distribution functions with each other, then we could actually say that there could be two reasons for why distribution functions could be different from each other. First of all, the, say, distribution functions between ya and yb could be different from each other because of the fact that there could be differences in the characteristics of the populations. It could be possible that the distribution of xa is different from that of xb. To come back to the example that we had before with respect to the wages of women and men, we should realize that in most Western economies these days, it is the case that women are higher educated than men. So therefore you may expect that, given the fact that we do also know that generally higher educated individuals also earn higher wages, so therefore at the moment that we're going to compare the wages of men and women with each other, then we should not be too surprised if we're going to see that the wages of the women are higher than the wages of the men, in the sense that the distribution function of the women is shifted to the right if we compare it to that of the men. And that is not because of the fact that there is discrimination. It's not that men are discriminated against women, but that's just because of the fact that we do know that even in the case that we're going to compare, say, high educated men and low educated men with each other, well, then also we are going to see differences in terms of the, say, wages of these men. So then it's also not that strange that if you compare a high educated group with a lower educated group, that the wages of the higher educated group in general are also higher. So therefore, the reason why there might be a difference in the distribution between, say, ya and yb could first of all be related to the difference in the characteristics of the populations. But there's also another thing that could be important, and that is that there could be differences in the conditional distributions. It could be the case that even the situation in which the characteristics of the populations are the same, then there could still be differences in terms of the distributions of ya and yb because of the fact that the conditional distribution, so the distributions conditional on these characteristics, they may be different from each other. Well, also here we can come back to the example that we had between women and men. It could be possible, even though I just said that that is generally not the case, it could be possible that men and women have exactly the same characteristics in terms of, say, their education, their age, their experience, and things like that. Suppose that we are going to assume that that's actually the case. Then it could be still possible that there is a difference in terms of the distribution that we observe from the women compared to the men. In general, and this is a little bit more related to reality, we could expect that men actually get paid better for the same characteristics as women. That's not to say that that actually should be the case, but that is actually what we generally observe. Men actually make more, even in the case that they have exactly the same characteristics as women. And therefore, their conditional distributions are in fact more in favor of them. They are shifted to the right, and that is the reason why we generally see that men actually have, say, distributions that are shifted to the right from those of the women. Well, we can look at this a little bit more into mathematical terms. This was, of course, just completely descriptive. We can also do this mathematically by using a very simple trick, and that is the, say, law of iterated probability. We do know that the distribution function of ya, evaluated in some y that we have over here, can be always written as follows. We can integrate over the characteristics, the, say, total support of this xa that we have over there, and then we're going to have the conditional distribution function of ya, conditional xa, equal to this little x that we have over here, and we are going to integrate essentially with respect to all the characteristics that we have over there. Well, this is just a law of iterated probability. But we can do, of course, exactly the same with respect to the B group that we have there. We would like to look at the distribution function of the B group. Then we can do exactly the same. We're going to integrate then with respect to the characteristics of the B group. Then we get the distribution function of that particular B group, or the conditional distribution function, conditional on the outcomes of xb, and also here we're going to integrate. And we immediately see that in line with what we have said over here, distribution functions are actually, well, determined by essentially the characteristics that an individual has, or that an individual group actually has, A and B group, but also it is based on the conditional distributions that we have over here. So therefore we could even look at so-called counterfactual distributions. What we could do is that we could ask ourselves the question, how would the distribution function have looked like at the moment that, for example, the, say, A group still is going to have the same characteristics as they have right now, so they have the characteristics of the A group, but they're going to have the conditional distributions of the B group. Again, at the moment that we're going to think in terms of women and men, well then this is a, say, counterfactual case in which we're going to ask ourselves the question, suppose that women still have exactly the same characteristics that I have right now, but suppose that they're not going to be paid as women, but suppose that they're going to be paid as men. What would in that particular situation have been the, say, hourly wages that we actually would have observed in that particular case among women? How can we get that? Well, the answer to that, it's not that difficult. The only thing that we need to do is that we have to replace, in fact, this distribution function that we have over here, we have to replace it by this distribution function that we have over there. So then we are going to introduce a new random variable. I'm going to denote it here by YAB in order to indicate that it's still the individuals with the characteristics of A, but with the, say, conditional distributions of the B population. So now we have the distribution of YAB, and it's simply equal to, well, again, the integral over the characteristics, but now instead of having the conditional distributions of the A population, we're going to get them for the B population. Take into account that this we can actually rewrite at the moment that we're going to look at distribution regression, because we do know that in distribution regression terms, we can rewrite this distribution that we have over here simply by this thing that we have over here. The reason why I'm going to write it like that is that you should realize now again that this is actually nothing else as a population mean. It's now in this case still a population mean with respect to the A group. Of course, even though we have here beta B, this is just a parameter, but we still have, say, an integral over the characteristics of the A group with respect to the density function of that A group, and it's this function that we actually are going to look at. So that implies that we can even write this as the mean of XA, or with respect to XA, of this whole thing that we have over here. And the reason why it's interesting to write it like this is because of the fact that this is a, as I said already, a population mean, so therefore it can be estimated by its corresponding sample mean. What we then are going to do is that we're going to sum over all the observations, of course of the A population, not the B population, with respect to this thing that we over here, and we divide, of course, by the number of observations that we have in the A population. So an estimator of our F that we have over there, the distribution function of, say, a population that we don't have, therefore it's a counterfactual distribution function, that we can actually estimate by this thing that we have over here. The only thing that we still need to do, and that we need to do, of course, with respect to the B population, is that we have to, in the first step, run a distribution regression for the B population at this Y level that we have over here. But apart from that, we don't need a B population, but the idea is now that what we're going to do first is that we're going to run a regression for any Y that we would like to do. We run a regression on the B population, distribution regression, in order to get these beta heads that we have over there, and then we simply plug them into the A population in order to calculate this thing that we have over here. And this is interesting. Again, at the moment that we're going to look at the example that we had with respect to women and men, this may be interesting because of the fact that at the moment that, for example, we're going to compare this distribution that we have with the distribution of the women, then we are going to see how women would have been paid at the moment that they would have been paid exactly like men. And the difference is essentially the difference that you have with respect to the distribution of the conditional distribution. So the difference in payments between women and men based on their characteristics. And this, of course, is not just related to differences in characteristics, but it's essentially here related to difference in payments. You could actually call this discrimination, wage discrimination, because of the fact that this indicates that only based on their characteristics, women are actually paid less on those characteristics than men are. So therefore, in this case, you're going to make a good comparison with populations which are exactly identical, but who are going to essentially be paid differently. Another thing that we could have done here is essentially to compare the distribution of the men with this distribution that we have over here. Then what we're going to get is a difference between men, well, with the characteristics of men, and paid like men, of course. And we're going to then compare that to the, say, distribution of, say, men if they would have had the characteristics of the women. So then we are going to see that that actually is related to a difference in characteristics. That has nothing to do in sense with, in terms of discrimination, but it's just because of the fact that individuals may be different in terms of their characteristics. So that means generally that we can actually decompose any difference in terms of distributions. So suppose very generally that we have, say, a random variable yb and a random variable ya, and again it's best to think about outcome variables that are more or less the same, but they are going to be drawn from different, say, subpopulations that we have over here. Of course, for any level of y, there may be a difference over here. And we should realize that we can always, say, decompose this, first of all, in a so-called composition effect. That's the difference between, say, the distribution of the B population minus what the B population would have had as a distribution in the case that they were still going to be paid like the B population, but they would have had the characteristics of the A population. And then in addition to that, we have the so-called structural effect, which is the difference between, say, the A population being paid like the B population minus what the A population would have had if they would have been paid like themselves. Well, we can do this in terms of distribution functions, but we can actually also do this in terms of quantiles. So also with respect to looking at quantiles between these two groups may be different, but there also we can, well, look at, say, the difference in terms of, well, what you actually get as a B population minus what you would have had if you, say, would have had the characteristics of the A population. And here we are going to look at what the A population would have had in the case that they would have been paid like the B population minus what they have at the moment that they're just paid like the egg population. Well, you should realize that no matter whether we're going to look at distributions or quantiles, the first usually is called the composition effect, and the last impact is usually called the structural effect.